Hey there. Today what we're going to be doing is determining that value of R experimentally. So what is the ideal gas constant? We know that the ideal gas constant R is a PV over NT relationship. If we can measure those four variables on a gas, we should be able to determine an experimental value of R. So let's get started with this. What we're going to be doing is reacting a piece of magnesium. Comes in a little ribbon. I also discovered in the larger form, it makes a wonderful cat toy because I actually found this on the carpet after the cat was attacking it last night. This is a very thin piece of magnesium. We're going to react that with hydrochloric acid to form hydrogen gas and magnesium chloride. We'll gather that hydrogen gas under a certain pressure, volume, and temperature, and we'll be able to determine R. So I've got my piece of magnesium ribbon. The first thing is to determine the mass of that magnesium. So onto the balance you go. It looks like a 0.100 gram piece of magnesium. How handy. Let's go ahead and record that data. All right, great. So now, putting my goggles on, I'm going to take the gas collecting tube. And again, it's open on one side, closed on the other, like a giant test tube, but it's also, maybe you can see, that it's graduated so I can read the volume, also called a eudometer. First thing I'm going to do is I'm going to fill this up with a little bit of hydrochloric acid. As I go back here in my procedure, I guess I'm jumping to 3, but that's fine. I'm going to fill this up with about 10 to 15 milliliters of a 6 molar hydrochloric acid solution. So I'm just draining it in, top of my eudometer. That looks pretty good. Now I'm going to go ahead and complete step 3. I'll jump back to step 2. I'm going to carefully fill this tube with water by tilting the tube and adding the water to the top. And because of the density gradient, I won't be mixing the hydrochloric acid with the water. The water will float on top to the very, very top. I don't want to trap any air in here. Perfect. Now, my next step, I'll go back to step 2, is to roll that little piece of magnesium up and tie it with a little bit of string. So the magnesium gets wrapped in a little coil, like in the picture. And I take a little piece of science string. Why is it science string? Because, well, it was a normal string about 15 seconds ago. I just made it science string. I'm going to tie that up here. All right, beautiful. I got my coil. Now I'm going to take my gas collecting tube, and I'm going to place that magnesium in the top, poke it down a little ways. Ah, perfect. So now the magnesium is sitting inside the tube, just like in the picture, but inverted. Now, normally I'd be placing a stopper, like here in the diagram, on the top, with a little hole in it to let the water escape. I think that also turned into a cat toy. So what I'm going to do is use one of my big fat fingers to plug the whole thing. Part of the reason I went into chemistry is because I have really big fingers. And I'm going to invert this into this overflow can here, full of water. So I invert it, and I push it all the way down. Now the hydrochloric acid is going to be falling where it hits the magnesium, and it's going to start creating bubbles. Ah, now that's better. So you can see the bubbles starting to form. That's the hydrogen gas. All right, actually my piece of magnesium came loose, and that's absolutely okay. You can see now that it's displacing the water with the hydrogen. Is that pretty? Here's my magnesium. All right, let's just let this reaction cook for a second, and we'll come back and see what happens. All right, great. So it looks like our reaction is finished. Now, to measure the volume, we have to equilibrate the level of water inside and outside the tube. I'll kind of explain why in a minute. But I can't measure the volume here. I don't want the water inside the tube above the water that's outside the tube. I'm going to get them level. And it looks like it's about 98.8 milliliters of the gas that's been collected. So let's go ahead and write that down in our data sheet. All right, great. Now, in terms of temperature, that's an easy one. So I have my thermometer in my house set to 70 degrees Fahrenheit. The water's been sitting out there, so it's the same temperature. So let's go ahead and record our Celsius temperature as 21 degrees. Again, that's going to be Celsius. For the pressure, I can just look at the weatherman's data for the day. He says the pressure is 29.93 inches, and it happens to be falling. Again, that's that's inches of mercury. In order to make that conversion, I can take the 29.93 inches I can take that 29.91 inches of mercury and convert it to millimeters of mercury. All you have to know is there's 25.4 millimeters in an inch, and we get a pressure of 759.7. Let's go ahead and call that 760 and record that. All right, the last piece of data we need is the pressure of water inside that tube. Because inside the tube, by the way, this is important, inside the tube we have the hydrogen and the water vapor together. So we're going to use Dalton's law to look at the total pressure, which happens to be 760, and we're going to look at the vapor pressure of the water, and we'll be able to determine the vapor pressure of the hydrogen. So according to this table, when it's 21 degrees Celsius, the vapor pressure of water is 18.7. Since we're not dealing in tenths, and this is going to be an addition problem, let's just round that to a vapor pressure of 19 millimeters of mercury. Great. Now we've got all our data. So let's talk about why I had to equilibrate those liquid levels and how I'm going to use Dalton's law here in a second. So what we said is inside the tube we have our hydrogen gas, but we also have a little bit of the water vapor also trapped in there. So the hydrogen pressure with the water pressure is going to equal the total pressure. We know that the pressure pushing on the outside, according to the weatherman today, was 760 millimeters of mercury. Now, if the pressure inside the tube and outside the tube are the same, in other words, if the pressure is 760 millimeters of mercury inside the tube as well, what do you think that means about the water levels? If they're both equal, that means the pressures have to be equal. So the only time I really know the pressure inside this tube is when I have the water level inside the tube and outside the tube equal. That way I can be sure the pressure inside the tube is the same as the pressure outside the tube, and I can measure the pressure outside the tube by asking the weatherman what that pressure is. Kind of an interesting little take on it. So, we know the total pressure. We know the vapor pressure of the water. How do we find this? Ooh, tricky math question. So, very quickly, we know how many grams of magnesium reacted. If we can convert that to moles and a balanced equation for the magnesium reacting with the hydrochloric acid to form the hydrogen and magnesium chloride, we can easily convert that mass of magnesium to moles of hydrogen. A little stoichiometry. We know our volume of hydrogen. That's got to be in liters, right? We know our temperature. Convert that to Kelvin. And we know how to get the pressure of the hydrogen when we know the total pressure and the pressure of the water vapor. That brings us down to writing a balanced equation for that magnesium reacting with the hydrochloric acid. Then we're going to calculate our experimental value of R based on the PV and NT that we solve for. Then, of course, we're going to have a result, and then compare that to the percent error that you should have based on our actual value, our theoretical value that we use in our calculations. Then there's some questions for you to answer. And that should be about it for this lab. Good luck, and I hope we came pretty close on this. I feel good about it. Have a great day.